So, more on series. What we did last time, we talked about the geometric series in particular, and we're going to do some more with that. But if you recall, the geometric series was this one, n equals 1 to infinity, r to the power n minus 1. And we found that this converges when the absolute value of r is less than 1. And what it converges to, I'll say in that case, this sum n equals 1 to infinity, r to the n minus 1 equals 1 over 1 minus r. So this formula you should remember, because it's going to come up a lot. And that you also have to remember this formula only applies when r is of absolute value less than 1. Even though, like, if r is bigger than 1, you can still try to use that formula and it will still look like it makes sense, but it's wrong in those cases, all right? Only when r is less than 1 does that formula even apply. If r, in absolute value, I mean, and if absolute value of r is greater than or equal to 1, then it diverges. In those cases, you don't use the formula at all. You just say the series diverges. All right. This is what we said at the very end last time. And actually, I'm tempted to put this formula here in a box, but actually I'm about to make it ever so slightly more complicated. So here's a very slight generalization. More generally, and this is very easy to see, sometimes what you're looking at, this kind of series, I said this kind of series actually occurs all the time, but often you see this series where each term is multiplied by some constant. And so the more general version of this looks like this. So it's the same thing, but all the terms have been multiplied by some constant a, and it's the same a every time. And what is that? Well, this. I mean, just from here, you can just multiply both sides by a. And so the right-hand side will say a over 1 minus r. This, I will write again, only is true when absolute value r is less than 1. This I'm going to put in the box. This is the general formula for the sum of a geometric series. And like I said, these actually do come up all the time in real life. For example, if you look at compounding interest, it takes the form of a geometric series and other kinds of things. All right. Let's just do some simple examples. Let me tell you just a little bit of terminology here. Oh, no, this is all right. This is where I want it to be. So how about, well, let me say it this way. Anything that looks like ar to the n minus 1 in a sequence, this is called a geometric sequence. And this is just a little bit of terminology. Geometric sequence. It's the same thing, but you're not adding them up. I just mean if you're just thinking about it as a sequence. And there's actually, in that setting, there's a name for the a and for the r. A is called the A is just like the first number that you get. The name for this is called the, where's it? Sorry. Here's what was going on in my head. I was thinking, I know it's the first term, but what do they call that in the book? And then I was looking at my paper. No, it's just called the first term. There is no special name for that. And R is called, this one, I remember, this is called the common ratio. And I'll say what I mean by that, why it should be called that in a moment. It's called the common ratio, all right? And A is just the first term of the sequence. For example, if I have the sequence using A equals 2, if A equals 2 and R equals 3, what does it look like? Then A times R to the n minus 1 looks like, if I were to write out the terms of this sequence, the first term is AR to the 0, then AR to the 1, AR to the 2, etc., right? That's what you get if you write out the terms, starting from n equals 1 as we always do. And if we use a equals 2 and r equals 3, what this looks like is just 2 to begin with. And then the second one says 2 times 3. The next one says 2 times 3 squared, etc. So if I just simplify a little, it's 2 and then 6, and then 2 times 9 is 18, etc. All right. And here you can see what the terminology, you can still see it at the very top. R is called the common ratio, but anyway, I hope you agree. A is really the first term, right? Right, A is 2, and that really is the first term. It's because the first term in a series like this, in a sequence like this, looks like A times R to the 0, which just equals A. So the first term is always A. The R is called the common ratio. R is, in this case, 3, the common ratio. And what that means, the reason it's called that, is because if you take the ratio of each term divided by the previous term, you always get the same number, and that number is R, which is 3 in this example. All right, so each ratio, which would be ratio, AN, I'll write it this way, AN plus 1 divided by AN. You always take sort of the next one divided by the previous one. In this case, that would be, the first time you would do that, it would be 6 divided by 2, which is 3. The next one, it would be 18 divided by 6, which is also 3. And the way that this sequence works, it will always be 3 when you divide one of these divided by the previous one. And that's why that number 3, which is R, is called the common ratio. Right? Each of those ratios, each one divided by the previous one, equals that number R. All right? And so actually it's easy if I give you, certainly if I tell you the A and the R, you can write down what the sequence is. But even if I give you the sequence, you can tell me what the A and the R is just as easily by figuring out what the ratios are. All right. Let's just look at some cute examples. I got a couple to try, and then I have some for you all to try. How about, let's find 2 minus 1 plus a half minus a fourth plus blah, blah, blah. So this is alternating signs and basically fractions with powers of 2, although it starts off with 2 and then 1 and so on, all right? And I will just say parenthetically, this is geometric. The pattern of this series is a geometric series. Now we have a formula for what you get when you add up a geometric series in terms of A and R. So we should figure out, let's first of all, find the A and the R. And those are basically always easy to find, provided that you remember how to do it. Anybody remember what's A? It is the first term. This is always very easy. It is 2, right? So in this case, A is 2. That's the first term. No special trick for that. And then the R is the ratio, the common ratio, which is always obtained by the next term divided by the previous one. And you should always get the same answer. So really all you got to do is sort of look at the first two, if you like, and you divide the next one divided by the previous one. So R, this is the common ratio. I'll take the second term divided by the first term, and you better include the signs. It should be negative a half. All right? This is the ratio, AN plus 1 divided by AN. You can do this in whichever term you want. You might as well just pick the first two, though, unless you have some good reason to use the other ones. All right? That is R. I did 1 divided by 2. You could have also done 1/2 divided by negative 1. That also equals negative a half, or any of the others. All right? Anyway, what's the sum then? So the series is the sum n equals 1 to infinity. If I were to write this, it's always A times R to the n minus 1, right? Which in our specific case would be 2 times negative a half to the n minus 1. The sum n equals 0 to infinity. And does this converge or not? Anybody remember the rule about when it converges? I said it a few minutes ago. Yeah?
When it's absolute value of r is less than 1.
Right. And so is that true here? It is true, yeah. It converges when the absolute value of r is less than 1, and in this case r is -1/2. So it indeed does have absolute value less than 1. So here, absolute value r, of course that is -1/2, is less than 1, so it converges. And what does it converge to? It converges to, and you just have to remember this formula, a divided by 1 minus r. In this example, that would be 2 over 1 minus -1/2. Make sure you keep the minus sign. If r happens to be negative, it matters. All right? This formula, remember, is a over 1 minus r. And then if you like, you can just simplify this a little bit if you want. 2 divided by 3/2, which is 4/3. That's what it adds up to. All right. Very nice, and typically fairly easy to work this out. Any thoughts about that one? I got one more, and then I have one for 2 for you all to try. All right, let's try one more. How about evaluate the geometric series? Evaluate. How about sum? Now this one is a little weird. 6 times 3 to the minus 2n. All right? N equals 1 to infinity, of course. This is a little weird because it almost looks like a times r to the n minus 1, but it doesn't actually. It's not n minus 1 up there. So the fact that this is not quite written in the way that we like, right? It's not quite written like a r to the n minus 1. Instead of n minus 1 up here, I see -2n. The fact that it's something times a power of something means it basically does have this format, but you have to do a little bit of work to figure out exactly what is the a and the r in this example, all right? And there's kind of 2 ways. One way to do it is to try to do tricks with this exponent to force this to look like an exponent of n minus 1, although in my opinion that's a little, I would rather not do it that way. I think the easiest way is to just write some terms and use the terms to find a and r in just the same way that we just did in the other example. And this is basically always going to be easy to do. I mean, sometimes you get weird numbers, but all you have to do is write some terms out and then find the a and the r that way. So let's write, and really you only need the first 2 terms because that's what it takes to find the a and the r. So let's write the first term, a1, and then the second term, a2. So the first term, using n equals 1 there, it'll say 6 times 3 to the -2, which if you prefer, this is 6 over 9, right? Which is 2/3 if you like. And then the second term is 6 times 3 to the -4. I just plugged in here n equals 2. And then this I'll simplify a little bit too. That would be 6 over 3 to the 4 is 9 squared, 81. And that doesn't simplify, does it? 2 over 27. Yeah, you can cancel 3's, right? Thanks. 2 over 27. Okay, great. And so, what is the a and the r? So a is, what do you say? Somebody shout it out. 2/3. It's just the first term. Yeah, that's sort of the easy one. The other one is also kind of easy, but I guess you have to work a little hard. The other one is the ratio, and remember, it's always like the second one divided by the first one. So here it'll be 2 over 27 divided by 2/3. And this, if you wrangle the fractions, those 2's can cancel, and I'll end up with a 27 in the denominator and a 3 on the top. So this is really 3 over 27, which is 1/9. That's the common ratio. All right. So it means this original series written in this somewhat inconvenient form, is the same as a, which is 2/3, times 1/9 to the n minus 1. All right, so our series is the sum of 2/3 times 1/9 to the n minus 1, right? this is what I meant by you can, in theory, use weird properties of exponents to sort of simplify this until it looks like this. Although, in my opinion, it's not always obvious exactly what steps you ought to be doing. To me, this is always easy to do. It took me a couple minutes just because I was saying every step out loud, but it's really, there's almost nothing to it. Anyway, this thing, what does it equal? First of all, you ask yourself, is the r in the appropriate range? Is the absolute value r less than 1? And it is, because it's 1/9. So we may use the formula. It does converge. This converges to, it's always a over 1 minus r. So in this case, 2/3 over 1 minus 1/9. Whatever that is. You can simplify that if you want to. I simplified it to 3/4 eventually. All right. This is how we do it. I got a couple for you all to try, and then we'll do something a little bit cute with these. You can do some interesting little things with these guys. So your job in each case is just to evaluate the series or say that it diverges. If the r is outside of the appropriate range, then the series diverges. So that's one. 5 over pi to the n, where pi is, the number pi. And how about that? See what you think. I'll come around and see how you're doing. Maybe I'll bring the bowl around again. Don't feel obliged to take one. Feel free to chat with your friends if you like. Quite different. Like if it wasn't a power, then it would be a cheese. Over here. All right. Feel free to chat with your friends. Everybody's working too hard. So good here? That's good, yeah. And this one's over here. Stay good here. I think it's next.
Oh.
Stay good here. So where are you guys from? New York City?
No, Westchester.
All right, I'm going to the airport. Still good here? Yeah. I'm going to start doing them up here. Everybody seems to be doing fine. It's just a matter of working it out, I guess. All right, can we chat about these? So the first one, as I was looking around, basically everybody was doing great. Write out the first two terms. They are those. The first term is 5 over pi, and the ratio would be this one divided by this one, and hopefully you don't mess up the fractions. I got 1 over pi. Anybody agree? And then, so my answer, this is in the appropriate range, right? This is less than 1 in absolute value. Pi is something like 3, so this is something like a third. And so I can use the formula. That means it converges to a over 1 minus r. And this, I suppose you could simplify in some weird way, but I would leave it like that. Any thoughts about that one? I think that's what I saw basically everywhere. And then the second one, I wrote down the a and the r for that one. This one, again, it's easy to get confused with the fractions and all that, but I got 1/3 for a and -4/3. In this case, -4/3 is outside of the appropriate range because the absolute value of this is 4/3, which is bigger than 1. And so this one, because of that, it diverges. You should not try to plug into the formula. Unfortunately, the formula still makes sense, so you may sometimes forget to check if it converges or not, and just jump straight up to the formula, and you will feel like you got an answer, but the answer is not correct. All right, excellent. We got some time left. I think we can talk about some what I would describe as cute tricks about repeating decimals. This is something that I don't know what kind of a kid you were. When I was a kid, I remember being very interested in repeating decimals, or I thought it was just the idea of the fact that some, 0.3 repeating is the same as 1/3. This was very interesting to me as a kid. And don't get me started on 0.9 repeating. This was an issue of great controversy on the playground, right? But this kind of thing, you can actually speak very intelligently about this kind of thing if you know something about geometric series. For example, how about the number as a repeating decimal? 0.5 repeating, 0.555. Maybe I'll put a little bar. That means the 5s repeat forever. What is that number? As a is that a well-known number, like as a fraction? Like 0.3 repeating is 1/3. Anybody happen to know what 0.5 repeating is? this is the kind of question that I would like to be able to answer. Actually, this is 5/9, because perhaps you remember 1/9 is 0.1 repeating. And so this being 5, I mean, it's 5 times that, basically. So this turns out to be 5/9. But how could you calculate that if you didn't already know that? That's what I want to talk about. We can actually calculate this. We can calculate it. Although this is a little strange to say, can you calculate what is that number? The answer is you just showed me what that number is. I mean, that is what that number is. Really, I don't really mean we can calculate it because that's what it is. I just mean we can write it in a more recognizable form, I suppose. But anyway, what's the connection between this and geometric series? It is because these numbers here, each digit of this number, maybe I'll just write out more of them. Each digit here represents like a place value, right? Like in an ordinary number, you have the tens digit and the hundreds digit or whatever. And if I was talking about, say, the number like 285, what I mean by there are place values here is what this number is, it equals 2 times 100 plus 8 times 10 plus 5 times 1. That is to say, that number 285 represents 2 in the hundreds place, 8 tens, and 5 ones, right? We can do the same thing with this decimal here. This is equal to 5 in the tenths place, so it's 5 times 0.1 plus 5 times 0.01, that's in the hundredths place, right? Plus 5 times 0.001, that's the thousandths place, etc., right? Does this have anything to do with geometric series? Geometric series are all about powers of number, right? It's always some constant times the power of something or other. Does anybody see powers here? It doesn't look like powers the way I wrote it, but any ideas? Yeah?
To the 1/2. Like
To the
1/10 times, maybe.
Yeah, you should think of this as 1/10. This is like 100th. This is 1,000th. Can we say those in terms of powers?
Isn't like 10 to the negative like 1 or like 10
Yeah, that's what I would say. These are, you could say, powers of 1/10, or you could say they are negative powers of 10, right? So I think it's a little more convenient for the sake of this problem to write them as powers of tenths. So this is 5 times 1/10 plus 5 times 1/10 squared plus 5 times 1/10 cubed, and so on. And when I say this plus ... really that means I am really talking about a series. This is a series. I'm adding together infinitely many things. And in fact, it is a geometric series because each one looks like a constant and then times something to a power. So this actually is a geometric series. And we can calculate it by using that formula about the a over 1 minus r, right? And that should tell us what the series actually adds up to, and I hope it's 5/9. That's the idea here. So this is a geometric series. Can we say what the a and the r is? I mean, those are the terms. We already have them written out. So can anybody say what's a? It's the first term, which would be 5 times a tenth, right? 1/2, yeah, if you like. 5 times 1/10, which is 1/2. It's the first term. And then the r is the ratio, so you have to sort of work this out. It's 5 times 1/10 squared divided by the previous term is 5 times 1/10. And everything cancels here except 1/10, right? The 5s will cancel, and then I have 1/10 squared divided by 1/10, only one of them. I end up with 1/10. Yeah, great. So first of all, does it converge or not? I think it does converge because the r is less than 1 in absolute value. It's 1/10. And then what does it converge to? We can work that out. So it converges to, here's the big moment, 1/2 over 1 minus 1/10, right? That's a over 1 minus r. A over 1 minus r. This is 1/2 over 9 tenths, right? 10 tenths minus 1/10. And then if we wrangle the fractions a little bit, it ends up looking like 5/9, which is what I said. Isn't that great? If only I had known about this on the playground, I could have resolved so many debates. I probably would not have understood this on the playground, but this is sort of the appropriate, sophisticated way to handle these kinds of repeating decimal questions that you may have about repeating decimals. All right. Let's do another one. Everybody's favorite one. Let's try 0.9 repeating. Right. Anybody happen to know what is that going to equal when we add up the series? This is the controversy on the playground. Perhaps you've heard. It equals 1. 0.9 repeating is the same as 1. It really is. And when I was a kid, somebody told me this, and the reason that they gave me is like, well, 1/3 is 0.3 repeating, and if you add 3 of those together, you get 0.9 repeating. But that has to be 1 because that's what you get when you add 1/3 together 3 times. And that was fairly satisfying to me as a kid, I think. Although I would say from a more sophisticated point of view, what they were saying is basically this: 0.3 repeating plus 0.3 repeating plus 0.3 repeating adds up to 0.9 repeating, which needs to be 1, and so that must be 1. Although I think my present point of view on this is there's something a little bogus about this. Like, are you really allowed to add numbers with the bars like that? I'm not sure. I mean, maybe, but these individual things represent infinite sequences of digits, and I'm not convinced necessarily that you really can do that at all. So this, viewing as a geometric series, is sort of the proper way to work this out for real. But anyway, so this, of course, is, I think of it as 0.99999, etc., right? And if I were to write this as a series, it looks almost exactly the same as the previous answer. So as a series, it is 9 times 1/10 plus 9 times 1 over 100, 9 times 1 over 1,000, etc. And then I can do the same business with the A's and the R's. So here A is just the first term. I'll write as 9/10. And then the R will be the next term divided by the previous one. So this will be 9 times 1 over 100 divided by 9 times 1 over 10. And when I cancel these guys out, I get 1/10. And actually, if you're doing this using base 10 numbers and a single digit repeating, the R will always be 1/10. Just the fractions will always work out the same way if you're doing a single repetitions of a single digit. All right. Anyway, the R is small enough so that it converges, and it converges to A, which is 9/10 over 1 minus R, which is 1 minus 1/10. That's 9/10 over 9/10, which is 1. This to me is a straight up legitimate proof that 0.9 repeating is the same number as 1. This is how you would work this out in full detail. Any thoughts about that? The other thing they used to talk about on the playground is, okay, then what about 0.00000 repeating forever and then a 1 at the end? What is that? Any? Did other kids talk about this on the playground? This is my playground experience. Anybody have a thought about that number? 0.0 forever and then a 1.
Would it just be 0?
Wouldn't it just be 0? I think my answer is yes, kind of. I would actually say there's no such thing as 0.0 forever and then a 1. Once you say forever, we're done here, right? You can say 0.0 forever. That's fine. That's 0. 0 forever and then a 1, I begin to doubt what you mean by forever. Like, there is no such thing as forever and then a 1, right? It can be forever. That's fine. Or it can be like, it can end with a 1 after finitely many digits, but there is no such thing, in my opinion, as 0.0 repeating forever and then a 1, all right? Great. Okay, I got one more interesting example. So this is not just for repetitions of single digits. Actually, every repetition of a single digit is some amount of ninths. Like 0.4 repeating is 4 ninths. 0.9 repeating is 9 ninths. But you can do this for any sequence of repeated digits. How about, let's try 0.7373, so where those two digits repeat. 0.73 repeating. This one is less obvious to say what you think the answer is going to be, but you can use the same methods here. The difference is when you write out the place values, it works out a little bit differently. If you just kind of naively, don't write this down because this is not going to go anywhere, but if you just naively copy what we just did, it would look like 7 times a tenth plus 3 times 1/100th plus 7 again, and then 1 over 1,000, etc. This is a real problem. If you're using different constants from term to term, then all of the formulas we've been talking about don't apply anymore. These formulas are only about the same constant every time, a times some power of something. So this exactly as written is not a good idea. The trick to get around that is instead to write it this way. 73 times 1/100th. So rather than saying 7 tenths plus 3/100ths, I write it as 73 hundredths. And then I sort of skip the next digit also and say it's also 73 times 1 over 100 squared. So this would be, I guess, 10 thousandths. You kind of are only using every other place value. And the reason you do it that way is so that you get that same constant every time, 73 every time. And then this will allow our usual formulas to apply, like so. All right? Just a simple trick. So can we work out the rest of the details and see what we get? So this will be, can we say what's the A? (73 over 100), right, it's always just the first term there. 73 over 100 is the A, and the R is the ratio. So I'll go 73 over 100 squared divided by 73 over 100. The 73's cancel. All we end up with is 1 over 100, I think. Right? And this actually will also be true. If you're ever doing this for repetitions of 2 digits at a time, the ratio is always 1 over 100. All right, anyway, this is enough to put it all together, right? The R is less than 1, so this will converge. And what does it converge to? Converges to 73 over 100 divided by 1 minus 1 over 100. So this is 73 over 100 divided by 99 over 100, right? And that would be 73 over 99. And you can check this in your calculator. If you just do this, divide 73 divided by 99, it really is that right here. 0.7373 repeating. All right, isn't that cute? I think that's interesting in my opinion. Any thoughts about that? In this way, you can actually calculate any repeating decimal. You know how like this maybe provides some closure. I don't know if you ever wondered about this when you were a kid. Probably your 5th grade teacher maybe told you any rational number can be expressed as a repeating decimal. And any repeating decimal, if it repeats at some point, it means it actually is a rational number. That is to say, if there are repeating digits, then there is some way to convert that back into a fraction. But your teacher probably never told you, how exactly do you do that? How do you take a repeating decimal and convert it back into a fraction? Actually, this is how. If I give you any repeating decimal like this is the method by which you can figure out what the fraction is that this came from. Right? Interesting stuff in my opinion. Any thoughts about that? You'll have some like this on the homework to check out. All right, I got one more thing to discuss in our remaining 10 minutes. So all of this was about geometric series. There is one, and the geometric series, like I said, comes up all the time. It is it's sort of, if you try to work out the math of compounding interest, it abides by the geometric series also, and also, repeating decimals and so on. Another common series which comes up, so another important type of series. This is not the geometric anymore. Important series. This is actually just sort of one specific example, but it's important enough that it has its own name and it's worth talking about, at least for the next 10 minutes. The series 1 over n added up. So if I were to write the terms, this is just 1 plus a half plus a third plus a fourth, etc. Anyone happen to know what this adds up to?
That's up to 2.
This is not quite the one which adds up to 2. So last time we talked about something which adds up to 2, and that was this. Only using powers of 2 on the bottom, this adds up to 2.
Oh, this time for
This one, he says, diverges, and he is correct. This one, I don't know if you've seen this before, but it's in my opinion, this is also very interesting. This series, if you only use powers of 2 in the bottom, it adds up to 2. This one, if you use every number in the bottom, it diverges. That is to say, this thing sort of adds up to infinity, if you like. This, when you add these numbers together, they do not converge onto a specific answer. They just keep on increasing forever. To me, this is surprising because these individual numbers that you're adding on, they actually do get smaller every time, right? It's a fourth, and then a fifth, and then a sixth, and a seventh. Eventually, these numbers that you're adding become very, very small. But it is still the case that when taken all together, they increase, this sum will increase without limit. All right? So that's what I want to spend, and we can explain this in the next 8 minutes. This actually diverges, or you could say, I mean, on the playground, I would say this adds up to infinity, although now as a serious adult, I don't say something adds up to infinity, I say it diverges, but this actually becomes infinite when you add together all of those fractions. All right, can we explain why? I think we can. Check it out. Here is why. This is not an obvious fact, and this little argument which I'm about to share is not something that an ordinary person would come up with. Like, it took people a long time to figure this out. But consider the partial sums. I hope you remember from last time. The partial sums are like, the first partial sum, S1, is just the first term, which will be 1. S2 is the sum of the first 2 terms, which is 1 and a half. S3 is 1 plus a half plus a third. Actually, I'm not going to talk about S3. I'm interested in talking about S4, though. This is 1 plus a half plus a third plus a fourth. And check it out. I'm going to do a very non-obvious trick, although I hope everybody will agree that this is valid. I am going to say this is this is greater than 1 plus a half plus a fourth plus a fourth. I just changed the 1/3 to a 1/4. And having made that change, it becomes smaller. That's because 1/4 is less than 1/3. All right? But what does this add up to? Well, this is 1 plus a half, but those 2/4 can add up to a half, right? And so this actually equals 2 now. But for reasons which will become clear, I'm going to say this is 1 plus 2 times a half. It equals 2. But there's 2 halves there. That's what I'm trying to say. All right? Check it out. I'm going to do a similar trick for S8. This is the first 8 things. So that's 1 plus a half plus a third plus a fourth. I'm going to go all the way down to 8 this time. 6th, a 7th, a 8th. And I'm going to do this greater than sign. And again, I'm going to replace the sort of odd ones. It's not precisely the odd ones. I'm going to replace the 3, make it up to 4. These other ones, 5, 6, 7, I'm going to increase them all to 8. So I'm trying to make it so that the denominators are all powers of 2. 1, 2, 4, and 8. So I'm going to leave the 1, leave this half. The third I'm going to make a fourth. And the 5, 6, 7, 8, I'm going to make them all 8. And each time this does make the fractions smaller because I've only increased the denominators every time. So this thing is still less. But this time I can group these guys. So I'm going to just simplify this. These fourths add up to a half. These 4 eighths also add up to a half. So what I see now is 1 plus a half, and then another half, and then another half, which is 1 plus 3 times a half. All right? This trick you can basically do forever. So if I go all the way to S16, I'm going to have, I'll turn it into something that looks like this, and then a big block of 16ths at the end. Specifically, there will be 8 16ths at the end, which will, again, all add up to a half. If you do the same thing on S16, you can show that S16 is actually greater than 1 plus 4 times a half. It's because you'll get the same thing, but then you'll have another block of 16ths which also add up to a half. So you get one more half from what you had before. All right. And generally speaking, so generally, 16, of course, that's 2 to the power 4. It is generally true that S of 2 to the n is greater than 1 plus n times a half. I was doing this for 8 and then 16, and then the next one would have been 32, I guess, which is 2 to the 5th. Each of these things is greater than 1 plus n times a half. And this part right here, this grows to infinity as n goes to infinity, right? N times a half. If you let the n become very, very big, this thing does not converge to anything. It diverges. And so what that means is the limit of the SNs diverges. Because each SN is bigger than this. At least some of them are. The ones with powers of 2, they're bigger than this. And this thing inside the box will become infinite as the n goes to infinity. So that means the limit of the partial sums diverges, which means the series diverges. So this, there's a name for this. This is called, I meant to say the name before, sorry. This is called the harmonic series. I'm actually not sure why this word harmonic is used. Anybody happen to know? I think there is a relationship between these fractions and music notes. Divisions of the octave are done by fractions 1 over whatever. But anyway, the harmonic series, sum of n equals 1 to infinity, 1 over n, diverges. This is another common example that comes up all the time, and there's no real formula to remember because it doesn't converge to anything, but you should remember that it diverges. All right, and I think that'll do for today. Thank you for your attention. I hope you have a good weekend, and feel free to take another candy on your way out.